Rob. Ooh, okay.
Okay, I'm trying to, there we go. I think that's the one.
There we go. Do you want the full screen?
I'm working on that.
Oh, okay.
Here we go.
Perfect.
All right. Can we see that?
Yep.
All right, so today what we're going to do is we're going to cover chlorinated paraffins compared to alternative chemistries. I know it got in there, it said replacement, but that's not what we're really doing. What we're doing is a study looking at different EPAW type of chemistries compared to chlorinated paraffins. And before we really get started into that, Univar Solutions is very serious about safety, and as a result, we do safety shares for our meetings. And so what I have here is on hurricane safety. The folks in Florida and along the Gulf Coast right now are very concerned about Helene and other places in the country and globally. There's big storms that you have to worry about. So some important aspects of that is having an emergency plan and ensuring everybody in your family knows the emergency plan as well, because if it's only one person, if something untoward had happened to that person, other folks are going to be a little bit confused. So you also want to make sure you go through it with all the family members. If you live in an evacuation zone, know the evacuation routes as well. Be familiar with them before it becomes a really bad situation so that you can move quickly to those zones. Recognizing the warnings and alerts, have multiple ways to receive that, up to and including a battery operated AM radio, so that if the power goes out, your phone batteries die, whatever that is, you still have a way to get information, which is very important, can be life-saving. Be aware of the risks, whether you're in a flood zone or not. Taping up windows, covering them, being away from them due to the high pressures that can come with hurricanes, and sometimes tornadoes as well can happen during that time. Have an emergency kit already set up. Have that. It's always good to have one in your car as well. And in your home, you want to be able to keep a 2-week supply of medications, batteries, chargers, flashlights, cash, because if electric goes out, ATMs aren't going to work. Keeping your important documents in waterproof containers is always a good part. And if you have to leave your home, it'd be good to do that. Flooding, as you know, can ravage these homes. So it's always good to be prepared before something bad happens. And around trees and electrical wires, you got to be careful. Obviously, you don't want to leave the home or the place where you are unless you absolutely positively have to, if it's emergency. And if you do, you've got to be really careful about trees and electrical wires, because the branch can fall, they can block the roads, the wires can hit. I've seen where people on videos online where people have been trapped in cars because electrical lines have fallen on their cars. So you want to be sure that you're very careful about that. Do not drive at all possible, once again, especially through flooded section of roads. I think we've all seen the news reports and videos of folks trying to drive through flooded areas and then having something terrible happen. Um, your car can be moved by less than 6 inches of water, depending on the current. So it can lift up and move a car. And if it's deeper than 6 inches, you definitely could end up being in trouble and being swept away. So it's just best not to go across the flooded road. After the storm, let professionals remove any debris and deal with broken trees, because we've also seen those videos of people trying to do it themselves and trees falling on their homes or their cars. So it's always best to leave that to professionals if at all possible. And finally, you want to document your home with photographs or videos. It's also good to have a written list. So if you do end up having any insurance claims, it's very easy to provide that to the insurance company and could help speed along your claims. So that's that. So let's get into what we're going to cover today. So we're going to talk about what is a chlorinated paraffin. Um, it's very simple. There's a lot of information for that. You'll see a lot of verbiage on the slides, but we'll just talk about it. And then we'll kind of cover, where it got its start, that we first realized chlorinated paraffins were out there, all the way through to, where we're kind of sitting today, tying that into the regulation stuff that's going on, stuff that you're familiar with, you may not be. Then we'll discuss our scope of work, because we've looked at this, and chlorinated paraffins has been on a lot of people's minds. So we've been able to discuss this and say, hey, this is something that we can do. We have the capabilities in our lab in Houston to do a great deal of testing and put that data together. And then we'll talk about some of the extreme pressure additives that we'll look at, and then we'll go over the data for testing, and then we'll go over our final thoughts. I'm going to tell you, there is a boatload of information in this presentation. We're going to try to go through it as quickly as possible. Once again, please, put questions, comments into the chat, and then we'll get to them after the presentation. So we're going to go ahead and get started. So when you look at a chlorinated paraffin, what is a chlorinated paraffin, right? Most people on this presentation probably know this, but chlorinated paraffins get their start from crude oil, from a paraffin base oil, essentially, where those lube cuts come from a distillation tower in a refinery. They are then solvent de-waxed. The newer technologies of hydrocracking and that type of thing to get the higher level group 2 plus group 3 base oils reduce or eliminate the waxes from those things, whereas the old style where you do the solvent dewaxing is where a lot of paraffin will come from, and that is still in a liquid form. And what they do is you take that paraffin oil and it's put into a reactor where they can manage the temperature and pressure, and then they introduce chlorine gas, which is very reactive, and which will attach to these these carbon chains. So that's essentially how you get a chlorinated paraffin. Very simple. The largest application generally is as a plasticizer and or flame retardant in PVC. They're also used in paints, sealants, and adhesives. The higher chlorine grades tend to be used as flame retardants in a wide range of rubbers and polymers. And of course, what we're kind of all interested in is the metalworking lubricants as EP, or extreme pressure agents. It's got a big usage there. Of course, what we're all familiar with is the short chain chlorinated polymers, paraffins, the mid chain chlorinated paraffins, and the long chain chlorinated paraffins. One thing to kind of point out about that is there's a slight differentiation in how Europe looks at these versus the United States. Although the short chain and the mid chain are the same, from a C10 to 13 for short chain and 14 to 17 chain for mid chain.
Cheryl? What happened to the quickie thing in my glucometer in my bathroom?
I don't know.
Okay. And then the long chains, this is where there's a differentiation from Europe to us. Europe looks at C18 to C30, and then but the EPA classifies long chain chlorinated paraffins from C18 to C20, and very long chains from anything greater than a C20 chain. So, and then when you look at the degrees of chlorination, typically you're looking at 40 to 70% by weight chlorine, and also different patterns of the alkane. Now, when we look at the history in particular, and I learned a lot of stuff, both Rob and I did some digging on these things, and come to find out, these things were basically discovered in 1830. That came about as a result of a party held in a castle in France. And what occurred that when it came time to light the candles, the party people ended up having irritated eyes, nose, throats, difficulty breathing. And one of the participants was a scientist who charged his son-in-law, who happened to be a scientist as well, to do an investigation to figure out what in the world happened. And as a result of the investigation, they learned that these paraffins had been charged with chlorine gas. So what happens when those paraffins were burning, they release hydrogen chloride gas. And as soon as those touch moisture, you get hydrochloric acid, which creates all the problems that the people had. So that's how they kind of discovered, oh, this is interesting. Now, the first documented synthesis of chlorinated paraffins was performed in 1858 by a Swiss researcher. So from that time frame, these things are really old. They're nearly 200 years old. And they've been around for a reason, right? Chlorinated paraffins, as everybody knows, have worked really, really well. Now, in the early days, like from the 1880s to the 1920s, they were used primarily for waterproofing, cosmetics, even a solvent for disinfectants. And one interesting fact I learned in the 1920s, they were even used in medicinal gum. So it's kind of crazy how these things have been utilized over history. Now, the initial production of these things from an industrial standpoint started in the 30s, and it really helped with the byproduct of chlorine from the production of sodium hydroxide. So the large-scale industrial use began in 32, especially with the introductions of chlorinated paraffins as extreme pressure added that is in lubricants. So when you look at the history aspect of this thing and the regulations tying in, we can see that back in 2002, these short chain chlorinated paraffins were highlighted by the ECHA, or the European Chemicals Bureau, and they were listed as PBT, which means persistent, bioaccumulative, and toxic. So that ended up being a problem, and we have the actual directives from that on there, so you can always look at that stuff. And in 2008, the short chain chlorinated paraffins were listed as priority toxic substances in Canada. Then in 2009, the US EPA was developing an action plan for phase out. Europe had a regulation that forced a reduction of production of them in 2012, which eventually led to a full production stop in European countries. Short chain chlorinated paraffins are still in some level of production, like in China, and you can have a distribution of molecules in certain things that they'll still be in there at a lower level. But finally, in 2017, they were listed as persistent organic pollutants in the Stockholm Convention, and essentially that stopped all their use from the main aspect of short chain chlorinated paraffins in the EU and the United States. Although in different parts of the world, it can still be utilized. Now we talk about today, more in what we're concerned with the mid-chain chlorinated paraffins. Short chain's gone. They worked really well, but had this problem of persistence and bioaccumulation and toxicity. A lot of studies were done on this. Now the mid-chain chlorinated paraffins in 2021 were added to SVHC, or substances of very high concern, not only to being persistent, bioaccumulative, and toxic, but they also had the VB labels that's attached to them, which is very persistent and very bioaccumulative. I had read a study from Europe that they were doing all different types of testing. They found it in mother's breast milk as well. So as you know, Europe's very conscientious about these types of things, and we tend to follow a lot of times with what they're doing. So all of that stuff was put into a study in 22 of September. The ECHA proposed banning them. As a result, a lot of things started to occur. Comments started going in. A group from the ECHA, which I was unaware of before studying to put this information together, was the SEAC, or the Social Economic Analysis Committee of the ECHA. So essentially what they did is they would do a review of all the information, and then also take in comments related to what kind of impact banning these substances would have on economies and the market. So based upon the work that they did, they were all for their proposed opinion piece was for banning it, limiting 7 years for oil related and 2 years for water related metalworking fluids, and then they'd have to be gone. But Ilma and among a lot of other people putting in comments, the SEAC revised that opinion. And ultimately, what they recommended and the ECH is talking about doing is a 10-year phase out of mid-chain chlorinated paraffins used in all metalworking. So no delineation between oil-based and water-based. It would be all metalworking fluids 10 years. Now, that 10 years does not start until the final restriction report is published, which it has not been published at this time. The expectation was that report would come out mid-year this year, but it could be as late at the end of the year and maybe even falling into the beginning of next year based upon all the things that are going on in Europe. But once that drops, there's probably going to be that 10-year time frame for what that would be. Now, with that in mind, that's what we were looking at, Rob and I and our chemist Jesse in our Houston lab, to think about, okay, we've got time, but we need to start looking at things of alternate chemistries. Is there really anything out there? We've all heard about things that can replace chlorinated paraffins, but the proof is in the pudding, and there hasn't been a lot of data or anything showing that they can actually be replaced, especially in the field. So we decided to take that on and start working towards, taking a look at these things from a phased aspect. So this is our phase one. And we have a project overview, and our scope of work was essentially looking at different tribological tests to start to begin to develop a database of information related to extreme pressure anti-wear type things that could be looked at as an alternative chemistry to chlorinated paraffin, not necessarily with the idea to replace them, but let's see what we can find based upon utilizing 4-ball extreme pressure wear, pin and V block, MTM, Timken OK, and doing all of these different types of tests. Our tribological assessment, the extreme pressure, lubricity, friction coefficient measurements, those types of things to begin the initial study to be able to determine what do we need to do. So we had to secure all the samples that we needed of chlorinated paraffins and alternative chemistries. We had to standardize how we were going to do this for both the standalone and combination tests if we had time. Even though we've got a boatload of information on this, we were under a bit of a time crunch for it. We had just under a month to put all of this together, do all the testing, analyze the data. So kudos to our senior chemist in our lab, Jesse Ziabro, and to Rob and the other folks involved in this to be able to help us get there. So we set these tests up. These are all in-house tests that we have in our lab, and we'll go into more detail a little bit later on that. And then obviously recording the results and observations and being able to analyze to see if there's any trends, anything that really stands out, make comparisons. But one of the things that we really wanted to hit on was we started looking for different studies out there to see, are we just copying something else essentially on our own doing this or what? But as you're going to see, we weren't able to find anything quite as comprehensive as what we've done, even in this initial phase. And quite frankly, that doesn't mean it's not out there and we weren't able to find it. But you're going to see we've got a boatload of data just on this portion. And at the end, we'll discuss a little bit about phase two. So this is where we're going to start getting into the meat and taters a little bit of this presentation. And I think you've heard enough of me talking for the moment. I'm going to hand it over to my peer Rob here for him to get started.
You have a beautiful voice, you do. And just want to tell you, as a chemist, here's the important thing. You want to use labware for your own personal drinking glass. So anyway, so I think we all know, phosphate esters, you can make it a lot of different ways, but P2O5 and, my past history and when I co-opted Elko. We made a lot of those. So yeah, and then so then you can substitute each one of those hydroxyl groups, and then preferably all of them. Then you don't have a free acid. And then you have chlorinated paraffin, which is basically what John described, just chlorine, atactic, cetiotactic, or otherwise it just lands on one of the to the carbon bond. And then finally we have sulfurized, mostly sulfurized fats are typically, triglycerides. So, but normally it's a disulfide, and that's going to be the one that's going to be what they call inactive. And then when there's trimer or tetra, then you have an active form that basically will stain copper strip in the D130. So those are the three. We're also looking at high molecular weight esters, because with the oxygen group on there, that's the polar part of it that's basically attaches itself in a chem absorption to the surface. Thank you. So yeah, so anyway, I think a lot of this is going to be pretty well known, but chlorinated paraffins, they're in the lower temperature range that they do their work. They form iron chloride or metal chloride, making that a sacrificial, part of the wear process, so that it smooths out the wear and lowers the friction. And they have superior EP performance, as we know. It's always like, well, if I'm having a problem at a customer, add chlorinated paraffin. Sulfur additives, that's a huge field there, because it's not just attaching something to paraffin. You can put sulfur on a whole boatload of chemistries. It's the highest temperature effective range. So it's the one that goes into the extreme situations where temperature is a problem. Again, I already talked about inactive versus active sulfur. And then you have strong EP and anti-wear performances. And then finally, phosphate esters, low volatility, prevents metal from seizing through its iron phos combination. And then, basically the phosphate esters also have some corrosion inhibition and things like that go with that. So we can move on to the next slide, because John's in charge of the slides. That's his job. I didn't know where I left my car keys. So I'm glad he's doing that. So this is our Artec. So a couple years ago, we had invested in this for our lab, and it's a modular unit. It's got a big frame that stands about 5 feet high. And then this is the working part of it. So
Yeah.
each
And we
module,
have,
good, John.
I'm sorry. Yeah, it's the MFT 5000 from Artec. So as Rob has stated, it's modular. We have a number of tests, modules that can go into this unit and be run. We'll be going through several of those today. So this is what those modules go in that we'll be showing. And you'll see pictures generally where it says Artec on it. So that's what this is going into. All the drives and the data linkages are in here. Temperature control, load control, all of that.
Thanks, John. Yeah, exactly. So here's a better picture too. Look, this is the 4-ball EP and wear test that we're going to talk about next slide. But here you can see that the modularness, and of course you have, all these connectors. There's no bearing flutter like you have in a regular analog version of this EP wear. So that kind of eliminates some of the noise that comes out of the test. And then everything's 80 converted with load cells. It can be, the neat thing about it is it can be controlled. Uh, you can do a lot of things with it. For instance, you'll see in our wear test that we started to look at stepping the load and stepping the temperature up, during the test, to give us different results. We have a profilometer. It's in the lower part of the picture. You can see we can also look at topography of it and depth, and a lot more things you can determine from it than just a microscope. So you can put filters on it to look at fraying edges and third body abrasion and all that good stuff. So if you have two products that are exactly the same in the wear test, then we dig deeper, and I look at what does the wear pattern look like? How deep is it? What's striations and all that, and try to read that and try to infer a little bit more data out of that. So that was our first test. So here we ran, so now we go into the EP test. So the EP test, as we all know, is basically only 10 seconds. And, so you don't get a lot of information. It's more about, it was all designed for shock loading. So it's not a non-steady state application, during for instance, uh, okay, I'm just getting these pop-ups that are throwing me off. Okay. So yeah. So anyway, for non-steady state. So, shock loading, let's say you're an excavator and you've hit some granite and all of a sudden the bearings in the scoop or in the shovel are like boom, and then that's all of a sudden the load goes way up for momentarily, and then you have to be able to handle that with your lubricants. So we wanted to qualify those. So here we did, and you'll see these same candidates throughout the different tests. So and quickly I'll just go through them this time, and then I won't kill you with it every time. So first one is the base oil. So everything I treated at 10% because I wanted to, and maybe it's an overtreat, but we wanted to have something that gave us a pronounced result to begin with, and then we'll optimize in our phase 2, et cetera, where we lower these things and see where they fall off. So we used a naphthenic base oil because we didn't want to worry about solubility problems or any kind of, two-phase or anything like that that would interfere with the purity of the test. Secondly, as we move across from left to right, you see we have 3 different chlorinated paraffins, and the only difference between them is the amount of chlorination. So on the left one, the A, that's the lowest, and then C is the highest. When we move into the sulfurized esters, we have 2 of them there. One is, a classic, sulfurized oleate, and the second one is a combination of different sulfurized products. And then we move on to complex esters, long chain, medium chain, based on, polymerization of, racinoleic and things like that. Further down the line, we have 3 phosphate esters. One's linear. The first one is a linear phosphate ester, and the other 2 are branched. So B and C are branched. And then finally, we squeaked in one test where we did a sulfur phos, which is classic. And, in our tribology, we did a combination of each of the 2 candidates that we liked, the A, phosphate A, and the sulfur compound B, at 10%. So here's the results. So the chlorinated systems, ascend from the lowest chlorination to the highest, and then, just like you'd expect, the sulfurized esters were both very good. And then the complex esters, depending on molecular weight, VI, et cetera, they perform differently. And then the phosphate esters, as we expected, the linear long chain phosphate ester performed the best, but the other 2 were pretty decent. The phosphate ester C wasn't all that great. And then finally, we have the combination of the 2, which is a tried and true marriage, and that did very well. Okay, we can go to the next slide. All right, so now we do 4-ball wear. So that 4-ball wear obviously is going to be more of a steady state type of a tribology. So you're looking at, constant speeds and constant, everything being constant. You're not loading. You want to look more at, you're thinking about hydrodynamic and maybe EHL kind of lubrication, mixed film, that kind of thing, because you don't have the extreme loads and you're going for a longer duration. So temperature plays a bigger part in the rise in temperature as the test is run for 30 minutes. John, why don't you tell them the parameters?
Well, that's an issue I have, Rob, that in Zoom, I can't see my notes.
Okay. All right. Well, we
So
ran
we'll
it.
add that later.
It's like 1 hour, the usual 40, it's 40 newtons, 1 hour, standard test. Here we ran, again, I'm just gonna point out the highlights. Otherwise we'll be here till, Christmas. But I think, again, we expected the chlorinated paraffins in this test to perform as they did, where where you have the lowest amount of chlorine is going to be your best candidate, where the higher the chlorine, the more iron chloride you form, the more fretting and the more third body wear you get. So that looks pretty good for what we know and commonly hold as true. And then we move on to the sulfurized esters, and the one that's has a combination of the B version is doing very well. So, joining several different sulfur compounds has a lot of synergy to it. And then we move on to the complex esters, which we would expect to do pretty well because that's what they're there for mostly. That's why I put them in there. And then the phosphate ester, again, if it's like an inverse between extreme pressure and normally it's in between extreme pressure, but in this case, the phosphate ester, which also is well known as an anti-wear because of its lack of sacrificially coating the thing, we did quite well again with the linear versus the branched materials. Phosphate C is a little anomaly. Okay, so now we did a modified version where we scaled up. We started at 5 newtons
15.
and 15 newtons, and we moved on throughout the whole thing to the end of the test where we did the ends where we normally end up at 40, and then we increased the temperature at each step. So this is like a step. It's not a linear progression. It goes from one step to the next. That's how the machine works. You got to program it that way. So interestingly enough, we get an inverse for the chlorinated ones. They jump out because there's an inverse expectant results compared to the first test. And I'll show you in the next slide, comparing the two, because I don't think anybody, including me, can remember what the last slide looked like. So there we go. So here you can see the inverse behavior of the chlorinated paraffin when you add heat and you break the thing in basically, and it probably has to do more with the heat of activation. That's our theory. I'm welcome to any thoughts on that for sure. Again, with this, in general, it did less well with the sulfurized esters. It did less well with the complex esters, and then et cetera. And then down, another one that just surprised me was that it did better with the branched phosphate esters than it did with the in the standard tests. So there's some inferences there that I'm not going to make at this point because we want to, but it gives us a direction. So now we can explore, why that happened, because sometimes it's unexpected, but that's what science is all about, learning from things that you don't expect and then figuring out why. Okay, next slide. We also did a Timken OK load, and if everybody knows the Timken tests, came from the bearing company, wanted to evaluate different metallurgies and different ways to lubricate and on, and they developed this test back in the Paleozoic era, and a long time ago. So that's another EP test here in ours. If you can see a close up of our actual instrument, we've got a sump there that feeds the race and the block, and and then running it at standard ASTM method for this test, and keep temperature's not controlled here. It's just it'll let it heat up if it has to. So it's a 10-minute test. Okay. So here's the results. Again, cascading upward, the chlorinated paraffins are behaving just like we expect, and their pattern is very recognized, except for that modified wear test we did. And again, the sulfurized systems, the B, which is the one that's a combination, again, shows that there's synergy going on between different, what's no? Oh, because that's different. The label's wrong, right? Okay. Yeah. I got it. Okay, and then complex esters, of course, aren't noted for their EP property, but surprisingly, the A did well, but that's a longer chain. And then the phosphate esters fall into the same category, the highest being the linear. And then our magic, mixture, which did just as well as the chlorinated paraffin C in this process. So then we decided, why not run pin and V, and that's, again, another extreme pressure test where gradually, as we all know, the old one just went dunk, 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 right? And you'd be in the lab and just the thing would drive you crazy. So ours is all basically electronically controlled, so we can control temperature. We recycle the fluid and filter it. So we pull out any kind of third body, particles that fall off that might increase wear and give us a result that has a secondary cause and not the pure cause of the lubricant. Next slide. Yes. Okay. So we know we have a high treatment level in all these, but the idea was that we would keep it as pure as possible with no interference. I mean, there's certainly many studies done on, glass, surfaces and things with interferometric studies and everything to understand how these things interfere with different additives interfere or compete. But in this case, we ran everything very purely because we wanted to get the pure results. I think at this point, we didn't, a lot of them passed 4,000, of course, as you would expect. Next phase, I think what we'll want to do is either lower concentrations to see where they fall off, and then also do some blends to see if that improves the, get some synergy out of it. So I guess this is a MTM mini traction machine. Back in the day, I was using we worked with NASA Glenn, and I had a pin on disc machine. And typically the claim is that you can measure friction directly without any second derivative calculations. So in this one, you have the fluid immersed. The disc is immersed in the test fluid, and then the ball is loaded onto the disc, and you can rotate the ball, you can rotate the disc, you can at different speeds, they can be at different ratios, so you can get a lot of variables about sliding. You can make it a sliding friction test, you can rolling test, so it's got a lot of versatility for looking at, and you can get a Strybeck curve out of it, which is kind of neat, which is what we have here. So as you expect, I mean, you're not going to be able to read all the tiny little dots and everything, but basically you're looking at, we tested them all. And as you would expect, you're going from static to kinetic friction, and, it's kind of a Strybeck curve. So essentially as you increase speed and um, the abscissa or x-axis is you're increasing speed, right? So speed times viscosity over load. Classic Strybeck curve. So as you increase speed, you lower the friction. And so we start out on the left at a lower speed, 2.5 millimeters per second, and then we end up at 1,000. So you can see that in these graphs, everything kind of convenes near the hydrodynamic region. Next. So here's the friction coefficients that are calculated. These are done basically as an average. So what it does is it compiles, it's like a sampling, like on your, sampling on any kind of a digital device, but it's 1,000 samples per minute. And all those are taken into account and then tallied up and then divided by the number of samples. And then you get the average coefficient of friction. So in this case, we have to look at it a little more closely to interpolate what's really going on there. But I think, and we can change the parameters to get more pronounced differences, I think. So, and that'll be in our next phase. And finally, as we move on to the final chart, this is everything. So everything compiled. So the things that jump out, phosphate ester A, had across the board looked really good. Let's look at chlorinated paraffins behaved, other than the anomaly in that one test where they were inverted, they behave pretty much the way you'd expect them. And then we had some surprises with the complex esters, and also sulfurized ester B did very well, which is, again, there's some synergy going on there between the different sulfur compounds. So that's basically all our data for now. So, yeah.
So when we get to kind of our final thoughts about all of this work, once again, as everyone understands, each test represents one property of lubrication. So it's not actually indicative of how it would work in the field. But when you put it all together, that table from the prior slide gives you kind of a clearer picture overall from what those tests did and what the data showed. And of course, the chlorinated paraffins are extreme pressure agents that performed well. The higher the chlorination on the chlorinated paraffins, with the greater loads, it did exactly as you'd expect it would do. And then things we really didn't expect was that the sulfurized ester B performed extremely well in several of the tests. So it outperformed what our expectations were. and that phosphate ester A also performed better than expected. So we did have some small surprises during this work that we did over the last month to be able to say, hey, what are we looking at? What is the data that we're doing to do this? Now, we're going to do a phase 2. And in phase 2, what we're going to do is some additional testing and also have some additional products. Now, we wanted to open it up to folks. You can put it in the chat. Are there any thoughts of what you would like to see from product perspective in phase 2, or if there's any particular types of testing? We have additional tests in our lab that we can perform, that we will be doing. For example, like a tapping torque, we'll do some other stuff as well to be able to get a better
SRV.
idea.
Yeah,
SR,
yeah,
yep.
there's a lot of, like looking at it from a chemist point of view, like I'm also watching this and listening to it, from the other side, and I'm saying, well, definitely we have a cutting tool module that we can look at in our system. So it's a rod it's just a milling type of system, but it recirculates and you can control temperature and all that good stuff. So we want to look at that. And then SRV, of course, for that back and forth, sliding movement that it was developed for piston against cylinder. And
Yeah,
we can
oscillating.
we can look at that oscillation and change frequencies, etc. And I think just optimizing, and lowering the concentrations to see where they fall off would be an interesting place to be. So we understand, how much, how little can we get away with and still get the performance we want. So that'll give us it all gives you a cascade of information that we put together and try to take all that to accumulate an idea of how everything's working. So that's going to be in phase 2. And we all welcome, being tribologists, all of us, I think we welcome any kind of ideas and suggestions, because I know everybody's done so many tests on this stuff and they're looking at it going, yeah, okay. So so we welcome that too. We want to get input.
Yeah, and of course, even though we've seen some promising alternatives from our initial research, there's a lot more work that needs to be done, obviously. And before you could ever talk about really replacing a well-known performing product like a chlorinated paraffin, you got to do field testing. The proof is in the pudding. So, you can have things, and we've all done it, where you've done testing in the lab, got these great results, then went into the field, and the results didn't quite equate to the field performance. So there's a lot of different variables that have to be taken into consideration. And I think, there's a lot more work that needs to be done before anybody can, very comfortably replace chlorinated paraffins worry-free, right? So we're going to go down the pathway of doing additional testing like we just discussed and see where things go. And then one last thing here, up in the right-hand corner of the screen, you see that QR code. I did want to point that out. You can learn more about our lubricants and metalworking capabilities by scanning that and going to that website. But we really appreciate your time. It was a bunch of information, a lot of data to
A
go
lot of
over.
work.
So we appreciate your attention.
Thank you. Thank you, everybody.
All right, guys, thanks for that. We've got a couple questions I'll start up with here. First question was, what was their application? What was their application in cosmetics?
Oh, I will find out. I think it was part of it was waterproofing, to deal with moisture, but I will get the actual answer.
Great. We also had one, I'm not familiar with this type of 4-ball tester. Is this a new type? What would you say the benefits are using this in comparison to the traditional 4-ball machine?
Yes. Yeah. It's the same. It's, 3 balls, stationary, 1 ball rotating with the, loaded. But the difference is that you can test, rather than having what I call analog, machine, you have, the loading is done electronically, so it's more accurate. You can change the loading. You can, like we did in the second test, in the wear test, we did where we stair stepped it from a lower load to the end load of 40 newtons. So you can do, so it has more variability, I think, than the standard. It's the standard test on steroids, basically, because now you can go ahead and change temperatures all over the
Right.
place if you want. So, I mean, because we know that, we all know that the common held, you got chlorine coming off first, then you have phosphates later, and then energy of activation, sulfur is last and highest. So is that completely true? From my experience of doing this 30 years, I'm going to say no, but I think that by being able to change temperatures and do like we did, we also showed that there was an inverse behavior of the chlorinated paraffins. So that right away indicates that there's something else going on.
Yeah, where in the under the tougher test, the chlorinated paraffin did a better job on the tougher part where the step loading and temperature rise was incorporated versus just the standard. So yeah, this test allows you can go to much higher loads than what you could do on a basic desk lab bench model. And of course, our temperature control, we can go to even higher temperatures. So it gives you more control of the variables. So
Yeah, you can change speed. You can do all the variables can be changed. So
yep.
because it's the same apparatus as you use as the EP. So it's got that range of the EP. So you can move it all over the place. So yeah.
Great. Is this study only investigating materials Univar distributes?
So far, that's what we started. We are in our next phase. We are going to look at a couple of products that we don't distribute at this time. So if there are, like we said, other products that have an interest in being incorporated into the study, we ask you put it in the chat so we can take note and see if we can get our hands on it to test it.
Yeah,
Great.
absolutely.
Did you also perform the Reichhardt test to evaluate the lubricity?
No. No, we didn't do that.
Right. A question, you may have already said this. What is the backbone of the phos ester A?
You can answer that.
Well, yeah, I don't. We definitely wanted to uh, anonymize the information so that we would just utilize the data and go from that perspective. We can always talk offline on things if needed, but that's what we wanted to do to make sure it was just about the data.
Please, could you remind me of the chemistry of the sulfurized ester A and B? I heard you mention olefins.
Well, look, A is going to be sulfurized ester A is going to be your standard fighting grade, high sulfur content with inactive sulfurized, fat, basically. So the second one is a combination of three different sulfurized products. They're proprietary. I don't even know exactly what's in there, but they're a blend of three different types of chemistry. So that gives you the synergy. But the first one's your fighting grade, sulfurized oleate that everybody uses, 40%, et cetera.
Do you have any testing that could simulate fine blanking?
Boy, I wish. That's uh, that's been a question. I mean, that's tough. I mean, you have the cupping test and you draw bead and all those that do that. We don't have a module that will give you that kind of movement. I don't, that's a tough one because I mean it's almost like a forge and a stamp at the same time. So that's a test that we don't have. So you'd have to just collect, unfortunately, you have to kick exogenous data from these tests and try to infer whether it's going to be successful in that. Like John put out, and I've known for many years when I'm going out in the field, it's like I've formulated things and I go out and thought, well, this had passed all these great tests. And I go out there and I go, wow, that was terrible. So, and just the opposite has happened too. So you just it's the like John said, the proof of the pudding is when you really get them out in the field. I think these tests normally give you a confidence that it's not going to be a disaster, and you've put your best foot forward.
Right. Have you thought about whether you would prefer to use phosphate ester or sulfurized ester in a formulation from a regulatory perspective?
Interesting. Well, yeah, that's a good point. I think, the phosphate esters that we have are basically considered sustainable, or they're derived from some bio-derived material. But again, you're talking about algae bloom and all that kind of stuff with phosphates versus a sulfurized product that's, doesn't cover that. So yeah, we thought of it, of course. I mean, I did 2 talks at STLE on sustainable metalworking fluids where I built them from scratch and showing you how you can do that. But yeah, I mean, as far as eliminating phosphates, I'd say we haven't looked at that
Yeah,
completely.
but I think, let me jump in here real quick. What we're
Yeah,
seeing
good.
also from some of the manufacturers are coming out with new phosphate chemistry that actually lowers the phosphate, but still provides, let's say, as good as or better than data versus the higher phos stuff. So that idea of reducing the amount of phosphorus in the chemistry is being worked on through these different suppliers. And obviously the phosphorus and the algae blooms, that's really mainly from agriculture, but we're getting looped into that a little bit. So I think you're going to see some reductions there, but still providing the protection that you need. Getting rid of one or the other, like Rob said, I don't know.
Yeah, I mean, it's just like with zinc and all those things. They just keep on trying to trying to use as little as possible and still get, satisfactory results. And that's a lot of people are working on that.
Great. Is there any consideration being given to evaluating combinations of the chlorinated paraffin alternatives to determine overall impact?
Yeah, absolutely. Yeah, yeah. I mean, overall meaning, you have to look at the whole umbrella. I think there's other properties that, that we're looking at tribological properties only at this point, but you have all the other peripheral properties, corrosion inhibition, fretting wear, on and on and on. So absolutely, that's what our next phase is going to be, is where we combine, different additives to see if we get synergy, and we already saw it in this test where we combined, of course, the sulfur phos classic combination that's been studied forever, and then look at some other chemistries other than just sulfurized oleates with different combinations too. I mean, this is the bare bones of the whole project at this point.
And looks like the final question is, so theoretically, if you used a highly chlorinated CP in a machine that worked at a low temperature light load, would you increase wear in comparison to using a lower chlorine content CP?
Well, that's $1 million question. I think based on our one study, you could infer something along that line. But normally, when I would formulate something with chlorine, I would have other materials in there. I mean, this is just base oil and chlorinated paraffin. So we don't know if that holds true when you start adding, fully formulating a material. You're going to have other stuff in there. So even something as simple as having a fat or something like that is going to attenuate that behavior. So, and I've seen that, in broaching and things like that are extreme. So I would say I would not infer that that's going to increase wear unless you just had a formula that had those two, base oil plus chlorinated paraffin in there, and only in this one test.
Right. Okay, I think that is it for the questions, unless anybody had anything further. Okay, well, I think that's definitive right there. That we're all set changing the screen there. Um, well, I'd like to thank Rob and John for their time today and presenting to us. We appreciate Univar partnering with STLE for this webinar. Thanks for attending today. We wish you the best. And remember, we do have a lot of great content in our STL catalog that if you're still interested in more, thanks a lot and have a great rest of your day.
Yeah, thank you.
Thank you very much.
Thanks, guys.
Thanks, guys. We
everybody.
appreciate it.
Bye.